The part of the scene that is in question is if James Bond can hold on to the grappling hook with both hands while being pulled up by the bungee cord. To figure this out, we must first know the potential energy of the bungee cord. To do this, we will use the formula potential energy of a spring equals 1/2 K times x squared. X will be how much the rope stretches. To find how much the rope stretches, we first need to find how high Bond's jump is. To find this, we must find the height of the dam. The dam that Bond is jumping from is the Contra Dam in Switzerland and is 120 meters tall. But Bond does not go all the way to the bottom. He stops at an outlet building that is 43 meters from the ground. So Bond's jump is 177 meters. The next bit of information that we'll need is how much Bond weighs. We're going to guess him around 165 pounds or 75 kilograms. For a jump of that height, a 51-meter unstretched cord is needed. That also means that the bungee cord will have to stretch an additional 127 meters. Now back to the math. To find the potential energy, we will need to set it equal to mass times the gravity constant times height, which is Bond's estimated weight of 75 kilograms times the gravity constant, 9.81, times the height of the fall, which is 177 meters. This gives us around 130,000 newtons per kilogram as the potential energy. Now that we know the potential energy, we can find K in the elastic object formula, which will be 16.16 newtons per meter. Now we can find the force that the bungee is pulling up with at the bottom of the jump using Hooke's law, which is F equals K times the stretch length, which comes out to about 2,050.17 newtons or 460 pounds of force. Because the bungee is supporting him, we can subtract off his weight, which brings us to 295.9 pounds of force. So unless Bond has super strength, the gun will be ripped from his hand and he will be launched back into the air. In this next famous James Bond escape in GoldenEye, we are analyzing whether or not Bond would actually be able to catch up to the airplane falling off the mountain. First, we need to find out how long Bond is falling to see if he and the plane reach terminal velocity. If you time how long it takes for Bond to get to the plane, it's about 19 seconds. It takes about 15 seconds for a skydiver to reach terminal velocity, so we can assume both Bond and the plane reach terminal velocity. By comparing their terminal velocities, we can figure out if Bond will be able to go fast enough to reach the plane, or if the plane is just falling too fast. The equation to find terminal velocity is as follows. Vt being terminal velocity, m is the mass of the falling object, g is acceleration due to gravity, cd is the drag coefficient, p is the density of the fluid through which the object is falling, and finally a is the projected area of the object. First, we'll find Bond's terminal velocity. We will again assume he has a mass of 75 kilograms. In the video, you can see he is in somewhat of a nosedive, so we'll estimate his frontal area as 0.6 meters squared, and the drag constant for a skydiver is 0.4. The density of the medium, the air, he passes through is about 1.2 kilograms per centimeter cubed. By putting this all together, we come out with 71.4 meters per second. That is on the upper end of how fast a skydiver falls, but definitely possible. Now we use the same equation for the airplane. We just have to change some dimensions. Biplanes like the one in the film can have a mass anywhere from 500 to 800 kilograms, but we'll approximate it to be about 600 kilograms. The plane is in a stalled nosedive, and we'll approximate its frontal area to be 5 meters squared. The drag coefficient for a subsonic plane, such as the one seen in the film, is 0.15. All the other numbers in the equation stay the same, so if you put all the numbers together, the terminal velocity for the plane comes out to be 114.3 meters per second. Since the plane is going 114.3 meters per second at terminal velocity, James would have to be going faster than that to catch up to the plane. We figured out that he is not going fast enough. He's only going 71.4 meters per second. So the stunt is not possible unless James is wearing secret jet boots we don't know about. Otherwise, in reality, this should have been James Bond's last jump. For our last 007 pulse-pounding scene, we will see whether or not Bond's bike would have been able to take the impact from that jump. First, we need to find out how high the jump is, by using the acceleration due to gravity and the time he was in the air. If we take the acceleration due to gravity, 9.81 meters per second, times the 1.5 seconds Bond was in the air, the seconds cancel, and we are left with the height of the jump, 14.715 meters. Next, we'll use the velocity formula to figure out what Bond's downward velocity is. The velocity formula is the square root of 2 times the acceleration due to gravity times the height. So this gives us the square root of 2 times 9.81 times the height we found earlier, 14.715 meters, which equals the velocity of Bond's downward force, which is 16.99 meters per second. Now that we have Bond's downward velocity, we need his horizontal velocity, so we can then find his overall velocity. We're going to guess Bond's horizontal velocity to be 40 miles per hour, but we need this to be in meters per second. To get 40 miles per hour into meters per second, we'll take 40 miles per hour times 1 hour over 3,600 seconds times 1,609 meters over 1 mile. After the units cancel, we'll end up with 17.88 meters per second as Bond's horizontal velocity. Now that we have Bond's horizontal and vertical velocity, we can find his overall velocity using the Pythagorean theorem. We'll take 17.88 meters per second squared plus 16.99 meters per second squared equals h squared. After you square root h, it comes out to be 24.66 meters per second. Now we must find how much force Bond and his bike must overcome. To do this, we'll use the equation force equals mass times acceleration. The dirt bike that Bond is riding in this clip is a heavily modified Honda CRF 250R. The original bike's weight is 230 pounds, but this bike has some extra cargo racks on the side, so we're going to round it up to 250 pounds or 113 kilograms. Now that we have the mass of Bond and the bike, we can add them together and times them by the acceleration to give us the force. So that means our force is equal to 215.66 newtons. The bike that Bond is driving in this clip can handle over twice as much force required for this jump. That means that this stunt is confirmed.